So hello and welcome to our talk, Hello from the Other Side, SSH over robust cache-covered channels in the cloud. So what is this talk going to be about? This talk will show you how you can use caches to circumvent the isolation of virtual machines. And it is not about software bugs. Software bugs can be patched easily. More it's about, we are showing an attack vector which we can use, and it's due to the hardware design of modern Intel CPUs. So it's really hard to replace a CPU, right? So this makes it even more impactful. We then will demonstrate how you can use our robust cover channel on the Amazon cloud. And yes, we do have a really cool live demo at the end. So what are going to be the takeaways? So cache-based cover channels are practical and they're a real threat. Well, we show that on the Amazon cloud as well, so they are real. And also, virtual machines, while they provide some isolation, they do not provide perfect isolation. So don't expect just because you're using a virtual machine, you're perfectly isolated from everything else, right? And as for now, there is no known countermeasure for what we present. So, but before we start, let's introduce ourselves, right? So my name is Manuel Weber. I am currently a PhD student at Graz University of Technology, and my interests lie in Internet of Things, in networks, and security-related stuff. You can find me on Twitter, on my Twitter handle Weber on Networks, and you can also drop me an email and my email address. Of course, you can also talk to me later after our presentation. And this is Michael.
Thank you. So my name is Mikhail Schwartz. I'm also a PhD student at Graz University of Technology. I really like the attacking stuff, I like to break stuff, I like to destroy all the new technologies and find flaws in it. You can also reach me on Twitter, you can write me an email, come to us after the presentation. We are here for the whole conference, so every time come to us, talk to us if you're interested in that stuff. Of course, there's also a research team, so we are part of this research team at Graz University of Technology, and especially on this talk, there were a lot of people involved in that. There's Clementine Maurice, Lucas Gina, Daniel Cruz, Carlo Alberto Buono, Kai Römer, and Stefan Mangard, all from Graz University of Technology. So first, you might have wondered what is a cover channel. So we had it in the title. Maybe not all of you know what a cover channel is. So in a cover channel, two programs would like to communicate. But the problem is they are not allowed to do so. What does that mean? So either there is no communication channel, like you have virtual machines and they're not connected to the internet, there's no shared memory, there's no access to the file system, no shared clipboard, no inter-process communication, so no way to communicate. So it's just not possible. Or the other possibility is you have a communication channel, but you're not allowed to use it. So imagine, for example, a firewall. So you have your application and it runs on a computer with internet connection, but you have a firewall preventing the application from accessing the internet. So the application cannot use this communication channel. And it might be stopped or just blocked. So we have to use a side channel, some other channel to communicate that is stealthy, so no one can see us and no application can detect that we are communicating. And we have a nice illustration for that. So we have two cloud instances illustrated as actual clouds in the image. On the left side, we have all our cat images stored, our precious cat images. And this virtual machine is connected to the internet. And we have a firewall there because we really don't want to lose our cat images. And on the right side, we have another virtual machine where we are the attacker and try to get the cat images. And on the virtual machine with the cat images, we have this gallery app which we also control. But it cannot connect to the internet. So we have to build a covered channel. So we exploit some hardware issues, for example in the CPU, to build another channel that does not go over the network, but as the cloud instances are running on the same physical host, they can communicate, for example, through the CPU. So there's a covered channel. It's a channel not meant to be used for any communication between two parties. And building such a covered channel poses a lot of challenges. So First of all, we need some side channels. So we need a way to communicate between the virtual machine instances. If we have this side channel, then we have to build a communication channel on top of the side channel to actually transmit data. Of course, there's a sender and a receiver, and we have to synchronize them. So it's actually possible to use the communication channel to send data from sender and receiver. And as with every communication channels, there will be transmission errors. Think of some wireless channels or on a wire. You will always have some errors in there in the transmission, and you have to correct them, because broken data is not really useful. And if we have that, we really like to have some application on top, like using SSH to communicate from the sender to the receiver. So before we can tackle all those challenges, we have to get a bit of background, and we start with CPU caches. If you take your normal computer, you have main memory in there, and main memory is kind of slow. So CPUs get faster every year. You get new generations of CPUs, and they will be faster all the time. But main memory cannot catch up with the speed of the CPUs. So main memory gets faster, but not as fast as CPUs get faster. So we have those caches inside the CPUs that buffer frequently used data. So data that is frequently used from the memory is stored in these caches, and they are really a lot faster. And every access to the main memory goes through the cache, and those caches are transparent to the operating system in the software. That means if you are a developer, if you're an operating system developer or an application developer, you do not have to care about caches. That's all handled in hardware. We cannot see that. So if we access the memory, data is loaded in the cache, and if we access it again, it will most likely be in the cache if it's accessed often, and we get it faster. So we do not care about caches, usually. But can we see caches? And yes, if we want to see caches, we can actually see them. So here we have a histogram of access time. So we just measured how long it takes to access a variable, some data in memory. And what we see here is how long it takes to access data that has to be fetched from the main memory, that is not cached. And we see a clear cut on the left side. It will never be faster than around 220 cycles. That's the memory latency, the memory bus latency. It won't be faster than that. And we can also see it's a logarithmic scale, so really most of the cases are around 220. And if we then access data which is in the cache, so that does not have to be fetched from the main memory, but can directly be served from the cache, that's faster. And we can see that's as fast as 50 CPU cycles to get data from the cache. And we have a small overlap there, but as it's a logarithmic scale, that's negligible. It's just a few, it's like 10 cases, and here are multiple million cases. So we can clearly distinguish from, with this histogram if data is already cached or if it has to be fetched from the main memory. And so we can actually see if data is in the cache or not. And then we have to look at how the cache actually works. So we have different levels of caches in Intel CPUs. We have a level 1 cache. That's the closest to the CPU. It's the fastest, but also the smallest. Then there's the level 2 cache. It's a bit larger, but also not that large. And then we have the most interesting last level cache. The level 1 and level 2 cache are per CPU core. So every CPU core has its own level 1 and level 2 cache. But the last level cache is shared among all CPU cores. So every CPU core can access the whole last level cache. And the last level cache is also sliced. So every core gets its own slice of the last level cache, but can access the other slices via a ring bus in hardware. And it also has a nice property. Everything that is stored in the L1 and the L2 cache is also stored in the level 3 cache, in the last level cache. So we can find all the data there, and the last level cache is really huge compared to the level 1 and level 2 cache. So if we then look at the details, how that data is actually stored in the cache, we have to look at the physical address of our memory location. So we take the address of the data, and then we have this physical address, and we can have a lot of bits there in the address. We ignore the least significant 6 bits. They're not used for the cache position. And then we have 11 bits in the physical address, bits 6 to 16, and that determines the cache set. So every slice in the last level cache is divided into 2048 cache sets. And this cache set is determined by these bits in the address. And as this is not complicated enough, every cache set is also divided into ways. So we usually have something between 12 or 16 ways per cache set. And to make it even more complicated for terms, we call that a cache line. So the data is then stored in such a cache line, and the cache set is deterministic by the physical address, but the way is not. This is determined by the cache replacement policy. And Intel does not disclose this function. There was recent work by Cruz et al. That reverse engineered this function. So we have a good approximation on how this works. We don't know if it's correct, but it works really well in practice. So that we now have a brief introduction to how the last level cache works, we will start with our first cache attack. It's called prime and probe, so we can actually do something with this information. And with prime and probe, we exploit the timing differences when accessing cache data and uncached data. We have seen that in the histogram before. We can clearly see a timing difference if data is in the cache or not in the cache. And with prime and probe, we are able to monitor exactly one cache set and monitor the activity in this cache set. The nice thing about the attack is it works on the last level cache, and the last level cache is shared among all the CPU cores, so it works across CPU cores. And we don't have to be on the same core. This is a typical setting for the prime and probe. We want to transmit data from a sender to a receiver, and we have the cache in the middle with every line symbolizes a cache set, and the receiver has a few addresses that map exactly to where all addresses map to the same cache set. So if the receiver accesses all those addresses, the cache set will be filled with the receiver's addresses. And if the sender wants to send something to the receiver, tell the receiver, hey, I'm here, then it just takes other addresses that map also to the same cache set. So the sender accesses addresses mapping to the same cache set. And as the cache set is already full, what will happen? The receiver data is evicted from the cache, it gets thrown out and replaced by the sender's data. And after that, it's again the receiver's turn, and the receiver will again access the addresses mapping to this cache set. And if the receiver accesses data that's still in the cache, we've seen it in the histogram, it's fast. And if the data is not in the cache because it was thrown out by the sender, it will see a slow access. And then the receiver knows, okay, the sender did something in this cache set, it tried to send me something. So that's the basic idea behind prime and probe. And with that, we would like to build a robust Covert channel. So we know the basics, and we want to use that in a way to build a real communication channel. And our goal is that we have this Covert channel that works across virtual machines. So we really want to communicate from one virtual machine to a different virtual machine. To have it really practical, we want to run it on the Amazon cloud. So if it works on the Amazon cloud, then it's actually practical and we can use it. And we can see that's a real threat because a lot of companies use the Amazon cloud. And it should be fast. So in academia, there are a lot of publications about cover channels, and they're often in the range of several bits per second. That's not fun to transmit data. If you just have a few bits per second, that's really slow if you want to steal or exfiltrate data. So we want to have multiple kilobytes per second on this communication channel. So it should be really fast, or comparable fast. And a fast channel is not enough for us. We also want it to be free of transmission errors. Because what's the use of a channel that is fast, but everything you send through this channel is then garbled and you can't use the data. So you really want to have it free of transmission errors. The data you send in should be the same that gets out. And we don't want to have it working only on lab settings. So that's also the problem with many academic publications. They work on lab settings, so if you have your own PC and run it there, it works perfectly. But if you go to the real world, like on Amazon Cloud, where you have a lot of noise, a lot of activity, they stop working. And we want to have it robust, so it works in the real world on the Amazon Cloud. And that's why we have to tackle a lot of challenges. So the first thing is this cross-VM side channel. And we require a side channel which works across virtual machines. So we need a new channel, where we can communicate from one virtual machine to another one. And we do not want to rely on software bugs. Software bugs can be patched. That's easy, and it's boring, because then our talk would be worthless if someone provides a patch for that. We want to exploit the hardware. That's much more fun. You cannot patch the hardware. Intel has to produce another version of CPUs or apply a microcode update. So it's much more fun to exploit the hardware that cannot be patched easily. So what can we use as a communication channel? So the memory is shared between all virtual machines. So that sounds nice. That should be a possibility to use as a communication side channel. And when we think about memory, we think of DRAM, the main memory. And yep, that has been done. We built a cover channel. Anders Fogg and I presented at Black Hat Europe last year. We built a cover channel using DRAM, and it worked. We could communicate there. It was not that fast, but it worked. And what else is shared? We have this shared cache. And as you've expected, this talk is about a cache cover channel. So we will be using the cache for that. And we can use prime and probe for the side channel. Because prime and probe works on the last level cache, so it works in the cache. Perfect. We know that the last level cache is shared among all CPU cores, so we can do a cross-core cover channel, and we don't have any requirement for any form of shared memory, so there's no need for a special setup here. We just need to build eviction sets and negotiate the used cache sets. So as we have seen in the animation before, we need those addresses that map to the same cache set, so that we can fill a cache set. And those addresses have to be in the same cache set and in the same slice of the last level cache. The problem here is that to determine the slice number is not that easy, because to calculate the slice number, you need all bits of the physical address. And for security reasons, you do not get the whole physical address on modern operating systems. You only get parts of it. So if you use this feature called 2 megabyte pages, then the hardware exposes the least significant 21 bits of the physical address to you. They're then equal to the 21 least significant bits of the virtual address, so we get the least significant 21 bits, but not the remaining bits. But to calculate the slice, we need all the bits. So that's a problem. But we can calculate the cache set, because it's bit 6 to 16. That's in the least significant 21 bits. We can calculate that. So we just build a set of addresses that are in the same cache set and in some slice, without knowing which slice it is. And then we can remove the addresses until all the addresses are gone which are in the wrong slice. So we check if they still fill the cache set, and if they do, it's fine, and we can remove another address until we cannot remove an address anymore. And then we're left with a set of addresses that fill exactly one cache set. So we unlocked our first achievement. We have this cross VM side channel. And with that, we can build a communication channel.
So now that we have covered how we can communicate with each other, we still need to find a common communication channel, because it does, if we talk to each other and I talk far away from you and you can't hear me, then it's no use that we have some basis to communicate. Also, we have to negotiate them dynamically, because we are on virtual machines that don't know from each other, so it has to work dynamically. Also, as we mentioned before, there will always be noise on the cache sets. So here you can see a quiet system and a non-so-quiet system. Even in a quiet system, you can see there is noise all the time. There are just small noise spikes. And if we then have some activity like watching a full HD video, we can see that we have much noise. This is actually pretty similar to wireless communication. So wireless communication channels experience the same problems that we have now. So if we have here now several examples of how noise or communication looks on a wireless communication channel. We always have a noise floor which is around minus 90 dB, and for Bluetooth we have some small spikes with much space in between. If we have a microwave, okay, no one uses a microwave to communicate with each other, but it blocks all communication. It's really strong and it just blocks all communication. You can see all the spikes that we have are really long and really strong compared to, for example, Bluetooth. Now, if we look at Wi-Fi, we have very small spikes, which are many, but small and not that long. So now there is an idea so that we can actually find each other from one virtual machine to each other. And the idea is, he who shouts the loudest will be heard. So basically, one party just generates a lot of noise on the channel, and the other party then listens and monitors the communication channel. And now, if we're listening on the correct channel, then we see that the noise level is always the same, because the other person is generating much noise. So if the noise level never falls below a certain value, we know that we are talking to our partner, that our communication partner is there generating this noise. This is also actually from a wireless communication. So my colleague Buano published this as a jamming agreement for wireless communication in Zigbee networks. So here we see first we have the normal noise floor and then the jamming agreement. We see that we raise the noise floor to a certain level and stay there for a certain period of time. The other party now listens on the channel and sees, okay, the noise floor never falls below this value here. And therefore we know that we are communicating with each other and that our partner is saying, yeah, I got what you sent me, I agree. And that works even if there is noise. So because noise is normally short and spiky, we just have to be longer than the longest noise we have to expect. And we see that it also works if we have Wi-Fi interference. So why do we need that? Because we just saw how we can talk to each other. Mikhail explained it before, use the cache. But now the sender has some cache sets which it can use for communication, and the receiver also has some cache sets. But how does the receiver know if the sender sends basically on channel 1 that this is actually channel 1? The receiver doesn't know that, so we have to correctly label the channel on the receiver side. Therefore, the sender starts with his channel 1 and primes it. Now, the receiver tries to find the channel 1, so it will also prime some of its channel. And now the sender looks, okay, did my colleague just find me and prime the same data cache set? If yes, the access time would be long, but it's fast, so we did not find each other. So now the receiver also checks, did I find my sender? In this case, no, we didn't. So the access time is fast, because we know if we access cache data, it's fast. So now we repeat that. We prime, the receiver also primes again a different cache set, because it tries everything it has through. and we did not find each other again. Then we try again, and until we find each other. And when the sender and the receiver prime the same cache set, the receiver will then evict all the data from the sender's cache set. So when the sender then probes its cache set, the access time will be long because its data has been evicted. Now, if the receiver also probes the same cache set to try to see if it found the sender, it will also experience long access times. So we know we found each other. So we have correctly labeled our first channel. So we have another achievement unlocked. We found each other in the cloud. Now, if we go and repeat that for all the channels that we want to use, we have agreed on common channels and our achievement unlocked. So what we did not talk about yet quite clearly is how are we actually communicating with others. So here is an illustration for that. We have the sender on the right side and the receiver on the left side. So as a first step, the receiver evicts all the cache sets it wants to use for communication. Now the sender looks at its data, which in this case is 0100100, and for a 0 we don't have to do anything. For a 1 we evict the cache set. Now if the receiver then accesses or probes the cache sets and measures its access times, it realizes for a 0 the access time is very fast, and for a 1 the access time is very long. So we correctly then have transmitted 01000100. Now let's look at another example, just for clarity. Now the sender wants to send 00101001 and again evicts all the cache sets. So the cache set number 3, 5, and 8. Now the receiver again probes all the cache sets and measures the access times and measures long access times on cache set 3, 5, and 8 and short access times on all the other cache sets, and therefore realizes, yes, we have this word transmitted. So now that we can talk to each other, we can also transmit files, right? If we can transmit bits and words and bytes, we can also just transmit files. So why don't we just take this picture of this butterfly and put it into our channel? Well, we did that, and it looked like this here. Of course, this is not usable, right? But still, we have another achievement locked. First transmissions, it wasn't usable, right? But still, we were fine. So then we thought, so now in academia it's always said, so now we have a communication channel. Now we can transmit some bits. We have some error rate which is abundantly high, but it's still fine. So we can just use error correction applied to this picture here, right? Because it's easy anyways. Error correction has been done and done beforehand on all the communication we have. But that's not how error correction works, because you always have to do some other steps first. Error correction is not a magic device where you put your data into and then the correct data will be just come out of it. So what we have to do first will be explained again by Michael.
So what we have to do here is we have to synchronize the receiver and the sender better, so that they actually are in sync and sending the data correctly at the same time. Because what we see here in this image are mostly synchronization errors. So in a perfect world, we have the sender and the receiver, and if the sender sends 100110, the receiver also receives 100110. That's the perfect world. That would be nice, but we're not living in a perfect world. So what is happening here? The sender sends some data, and some of the data gets lost. So why does it get lost? The sender is just a normal program sending stuff by evicting cache sets. And the receiver is also a normal program running. And as you know, the operating system schedules programs, so not every program is running all the time. If the sender now runs and sends the data, and the receiver is at some point not scheduled anymore, so it's just not running, then it cannot receive any data. But the sender does not know about this. It's completely transparent. And the receiver just misses data. And that's not like 1, 2, or 3 bits here. It's a long time, so it can be up to multiple milliseconds, and we're losing like 100 to multiple thousand bits. If it would be just 1 or 5 bits or something, then it could be corrected by error correction. But if we lose thousands of bits, then that can be corrected with any error correction. And we have another case That's the opposite case. So the sender at some point sends and then is interrupted by the operating system. So it cannot send anymore. But the receiver happily receives data which the sender never sent. But the receiver doesn't know that the sender is not running. It's just not scheduled by the operating system. And the receiver receives data. And what does the receiver receive? It's garbage, of course, but it will be, in most cases, 0. Because the sender is not running, it cannot evict cache sets. So it's always not evicted, and not evicted means 0. So the receiver receives a lot of zeros, like thousands of zeros. And that's also something typical error correction cannot correct if it has so many insertions. And only sometimes we have these actual substitution errors. So that are the errors which can be corrected by your typical error correction mechanism, where we just have bit flips. So we wanted to send a 0 byte, receive a 0 bit, receive a 1 bit, or send a 1 bit and receive the 0 bit. That can be easily corrected by an error correction code, but that's just in a few cases. In most cases, it's that either the sender is not scheduled or the receiver is not scheduled, and we miss a lot of bits or have a lot of garbage bits. And we have to cope with that. So to cope with deletion errors, we use a request to send scheme. And you know that from typical protocols like TCP, we use packets. So we chop up our stream and use packets for that, and use 12 bits packets, and we add a sequence number. Use a 3-bit sequence number for the packets. And the receiver acknowledges this package by sending the next sequence number. So it always receives a packet and requests the next packet from the sender. And the important observation is here, if we think back, the insertion errors are almost always 0. So we just insert zeros here. And if we are able to detect those zeros, those additional zeros that do not belong there, we can detect many or even most of the insertion errors. So what we did, we used an error detection code. That's just a code that detects error. It cannot correct anything, but detects the error. And in our case, we used the Berger codes. It's a really simple error detection code, and we added it to the end of the packet. 4 bits for error detection. And the Berger codes are really trivial. Any one of you can come up with that. They just count the number of zeros in a word. So this is a nice side effect. There is no 0 word anymore. So if we receive a bunch of zeros, we know that it's wrong because the Berger code counts the number of 0 bits in a word. So if everything would be 0 in the packet, then the error detection code is a high number. And if we just have zeros, we know it's wrong. So with that, we can detect a lot of insertion errors, or most of the insertion errors. And now we have this achievement unlocked, we are able to detect interrupts. We can cope with the deletion errors, and we can cope with the insertion errors. So the protocol looks something like that. We have the sender and the receiver starts, because it's a request to send scheme, and the receiver tells the sender, give me the packet with sequence number 1. So the sender sends back packet with sequence number 1. The receiver acknowledges that by requesting packet number 2. Sender sends packet with number 2, but the receiver is not scheduled, so it cannot receive the data. That's why the sender just continues resending the packet until it's acknowledged, so it again sends data with sequence number 2. Then the receiver acknowledges that, because it's again scheduled, and the sequence number 3, but the sender is not scheduled now. So this request gets lost, and the receiver tries again until the sender answers with the correct packet. And that goes on, and as we can clearly see, we can cope with all the descheduling where either the sender or the receiver is not scheduled. That's why we have another achievement unlocked. We actually synchronized the parties. So we have the sender and receiver in perfect synchronization now. And we do not lose packets or get garbage packets. Okay, remember this picture? We had this nice butterfly, or what remains of the butterfly, without the synchronization. And now we use it with our scheme, and it looks much better. So we can actually see the butterfly here. But wait, it looks a bit noisy, right? Let me zoom in there. Wow, there are funny pixels in there with strange colors that do not belong here. So that are the actual substitution errors, where we flipped some bits in the transmission. So can you enhance that?
Oh yes, we can. So now this is actually where the error correction comes in, because this is the case where you should use error correction. So what you saw are the substitution errors that remain, and these can be corrected using forward error correction. We chose to use the widespread Reed-Solomon codes mainly because they're rather simple and they're very efficient. There are some other codes that may perform better, but they also use more system resources, which is why they're not really usable. Reed-Solomon codes are perfect because they do not use much for encoding and only cost a bit when decoding. So when we talk about Reed-Solomon codes, we have to know that packets are made of symbols. And the symbol size is for us pretty naturally because we have 12 bits as physical words, as you remember. So we chose, okay, our RS symbol size is 12 bits, which is then an RS word, or Reed-Solomon word. And with that, due to how Reed-Solomon codes work, the packet size is given. So the packet size can be calculated by 2 to the power of the symbol size minus 1, which equals then to 4095 symbols. And also something that is nice when dealing with Reed-Solomon codes, the packet, when encoded, consists of the actual message and then following the error correction symbols. So how is this done? Actually, Reed-Solomon codes are just a simple matrix multiplication. So we have our data in a vector, then we have an identity matrix together with the error correcting polynomis and multiply them with each other, and voila, we have then the encoded data, which contains the data itself, and as promised, the correction codes. So that sounds a bit abstract. So let's look at that with another example. Here we have a penguin, like you may find in wildlife distributions like Linux, and now we want to encode that. So what we now expect is we have the penguin chopped up, and in between some error correcting codes. So, and this is actually what happens. The penguin is chopped up, sliced, and then in between we have some error correcting codes. And you can see actually how big one packet is if you look at the size of one such slice. And of course we then transmit more data. So to be better safe than sorry, we chose to use 10% error correcting code. That sounds a bit smart, right? A bit much, right? But with 10% error correcting code, we can only correct 5% errors. Also what you have to know is that Reed-Solomon works on a symbol basis. That means if we have 10-bit flips or 1-bit flip in one symbol, it doesn't matter. 1-bit flip is enough and the whole symbol is wrong. So we can correct 5% of broken symbols with 10% error correcting code. Actually, we normally don't need that much. Normally we only have 1 to 2% of errors, and therefore we would need only 2 to 4% of error correcting code. But due to the nature of the system, sometimes you have spikes in system load and then you have more noise. And due to that, you have to also calculate with that. And therefore we chose to use 10% and not just 4% of error correcting code. So we can deal with system noise spikes. So how does it look like now? We have, if we use 10% error correcting code, we have 3,686 data symbols and 409 error correction symbols. And now we can actually look at it like we would look at a normal communication in between, well, a sender and receiver with a physical and a data link layer. On the physical layer, we have our data with 12 bits. We have then our sequence number, which contains 3 bits, and our error detection Berger codes. Now, only the data itself then is used for the data link layer packet, and it then composes together with the parity the whole Reed-Solomon packet. So we have another achievement unlocked. We got rid of all the noise. We are now error-free. But as I mentioned before, it costs a bit to do error correcting. So let's look how well we do in speed. So you all remember dial-up, right? With 56 kilobits of high speeds and a noise that woke everybody up in the middle of the night. We are faster than that. We are also faster than its big brother ISDN, which had 128 kilobits. Then we have GPRS, which is a tad bit faster, which has 144 kilobits, and we are also faster than that. So the Amazon EC2 cover channel actually features 362 kilobits per second, which is pretty nice and pretty close to Edge, which is still used in some rural areas, for example in Austria. And if you let our cover channel run on your native system, it actually runs at 600 kilobits per second. Of course, how fast the cover channel is depends very much on the hardware you use. The latest hardware is faster, so Intel is actually helping us. They're producing faster CPUs, so we have a faster cover channel. So, and also to put it into a perspective, above fast is then 3G, which is around double as fast. So now that we have this cool, robust, error-free cover channel, let's do something useful with that, something cool.
Yeah, let's use it for something. We have it's fast and it's error-free, as Manuel said. So make it useful, do something with it. And what could be more useful and more fun than a remote shell? And what's cooler than having a remote shell without network access? And which remote shell should we use there? Of course, our all-time favorite, let's do SSH. And the only prerequisite for SSH is just TCP. So it should be quite simple, right? Just implement TCP over cache. You should actually get an RFC for that. It works pretty well. So we have this scenario here. We have our two virtual machines on the same physical host, the hypervisor scheduling the virtual machines, and the shared last level cache. And we know we have our cover channel here with the prime and probe, so they can talk, and they talk through the file system. Right now we were able to send the files, the beautiful pictures, and then we just added another layer, because we're lazy and we know another layer of abstraction solves all the problems in IT. So yeah, just put another layer on it. Then we have a TCP socket to file system layer, and then we have actual TCP sockets on both sides of the virtual machine. And then it's easy. We can use any TCP client and TCP server software, and they just talk through the last level cache. They don't know where they are talking through. It seems like a normal internet connection for them, but they're actually talking through the cache cover channel. So we have another achievement, TCP over kind of anything. So we can get TCP over the cache running. And it works really well. So we tried that. We tried to establish an SSH connection between two instances on the Amazon EC2 cloud, and without noise, it worked perfectly. And then we tried to see what's possible there. So we started another virtual machine, a third one, and run the stress tool there. And the stress tool with -M8 allocates and deallocates a lot of memory all the time with 8 cores. And it still works. The connection is stable. And then we thought, okay, let's start a web server on the VM and DDoS the web server there with our own computer. So we had 100 connections, downloading, uploading stuff all the time. And the connection was stable. And I said, okay, let's do a web server on all the VMs, on the sender and the receiver and on the third VM, and have a lot of connections and download and upload stuff. And it was still stable. So we really have a robust cover channel. Then we started to stress the VMs, and then it got a bit unstable. So if you really stress all the VMs there, then sometimes the connection dropped. And then we thought, okay, let's fall back to Telnet, because we have TCP over anything, let's use Telnet. And Telnet worked, even with the stress, but sometimes bytes were corrupted. So we would not really use that. Imagine you doing some ls or cd, and it corrupts the bytes and it gets rm, and you delete the file you wanted to view. It's not good, but if you dare to try, Telnet works even with corrupted bytes. So we have a really nice TCP proxy now from across 2 virtual machines. And our final achievement, we get this error-free cover channel from one VM to another VM on the Amazon cloud. So what is the conclusion here? Cache cover channels are actually practical. So we can get really fast error-free transmissions over the cache. It's not detectable by any firewall intrusion detection systems. It's completely stealthy. It's noise-free, it's fast, it works in real-life scenarios. You can run it on the Amazon cloud and with web servers running in parallel, so it's really practical. And a lot of academic papers says, okay, protection against such cover channels, just apply noise to the operating system. Then nothing will work anymore. That's not true. So we had a lot of noise, and if you implemented error correction and synchronization, you can have a lot of noise and it still works. So noise is not a countermeasure against such cover channels. And you can try it yourself. So we provide you a small tool that implements the cache-based jamming agreement. It's on GitHub. You can download it, compile it, run it on your favorite cloud provider, on your company cloud, wherever you want, and see if your cloud is vulnerable to that. And it has a documentation on the GitHub page, and also the white paper will be, I think it's tonight, it will be published by Black Hat with a good description. And now we come to a live demo. We would like to show it live on the Amazon cloud. Finger crossed it works. So please, Manuel.
So here you can see that we are already connected to our two virtual machines, and here we have a local shell. What you can also see is we have two different IPs, so we are on two different virtual machines. This one is going to be our server, this is going to be our client. So what we are going to do is we are going to transmit a video over the cache. And which video would be better than Adele's "Hello from the Other Side," right? So let's do that. So first, here we have our server which will transmit our video, which is just called video. So here we have our client, which then pipes its output into a netcut session, which listens on 8080 for its partner. And here we will start the other part of the netcut session, which then pipes its output into VLC. We also added some caching just for safety, which is the file caching, because, well, what is if something happens? And also we added, for your enjoyment, a subtitle file so that you can truly understand the text. So let's start. So we can see the server boots up and then waits for its partner. And they started transmitting. We're still caching, but it should be about, yes. So hello from the other side. Remote shell through the cache this time. Through your system, steal everything that I want, and as my channels covered, you'll never know. Hello from the outside. I don't even need network rights. I'm not even sorry I broke into your machine. Your cache noise pattern, it clearly doesn't save your VM anymore. Thank you very much. So here we now see the speed. We were actually faster than we told you before. We achieved this time 392 kilobits per second. and we were totally error-free. So what you just saw here, we actually extended Amazon's product portfolio. We now provide Amazon, Prime, and Probe. So I think we still have time for some questions. The video, so we have also provided a demo video which we will upload and which Mikhail will then tell you over his Twitter account. And you still see here the link to our tool. Now if there are any questions, please. Yeah.
Cache are you using?
So on the Amazon cloud we have 20 megabytes of last level cache, and that's a lot. And we actually use only 19 of the cache sets, so we have 2048 cache sets per slice, and we have 8 slices on the Amazon machine, so it's just 0.something%. So
you could wrap that up?
We tried, yes. So we could make it kind of faster by using more of the cache sets, but then it's more prone to errors. So the more parts of the cache you use, because other applications on the system also use the cache and the operating system, and the larger the amount of cache you use, the more error prone it is, and the more error correction you have to use. But yeah, I guess it can be faster. We did not experiment how fast it can get. We mostly tested on our lab machines before, and they had smaller caches, so that was kind of a good number of cache sets, which gave us really good speed. But yes, I guess it can be faster. If you have larger caches, like on the Amazon cloud, then it can also be faster if you use larger parts of the cache. Yes?
How do you make sure you have to fill it level cache until how long?
That's a good question. So the question was how to make sure that it's in the last level cache and not only the L1 and L2. Intel CPUs have a nice property that all the data that's stored in the L1 and L2 cache is also stored in the last level cache. So the last level cache contains all the data. So that's why it works really well with the Intel CPUs. Everything is in the last level cache, and AMD does not have that property. So we don't know of anyone accomplishing that with an AMD CPU. So you might be more secure with an AMD CPU, no idea, but no one uses that. So, and we did not find a lab machine at our university to try it, so it's an open research question. Did that answer your question?
Is there a reason why you use 3 bits for the sequence number? And also, is there any thoughts on using compression and compression?
So the question was why we use exactly 3 bits of sequence number and if we could use any compression. We used 3 bits of sequence number because it worked. So that was our first try. And it worked perfectly, so we had no problems with that. But of course you can increase the length for the sequence number.
But wouldn't it theoretically be better to reduce the length so you can send less data to be picked up? So you theoretically need 1 bit.
So you only want to use 1 bit for the sequence number. Yes, but if you miss a few packets, then it's better to have a higher sequence number to know where exactly you left off, so which packets are lost. Because it can be due to a high noise rate or a lot of scheduling that you miss a lot of packets and not only 1 packet. And then you can continue where you left off and don't have to search for that or try again.
Also, we did not just use the full spectrum of the 3-bit sequence number, but we added some security for this sequence number as well.
We have. So we also, for the...
Because otherwise, of course, they use the same channel. They are prone to the same errors, but we cannot use error correction codes for the X. That wouldn't work.
Yeah, so we also use some error correction inside the sequence number. And so we can't even use all the bits in the sequence number. But you could use a longer sequence number. But if you only use 1 bit and you get a bit error in the sequence number, then it's kind of broken. So we're better safe. So with all the numbers, we are on the safe side, and we're pretty sure if we use higher numbers for cache sets, for sequence numbers, error correction, you can get better speed. But yeah, you can try that if you want. We didn't experiment with that. And for the compression, of course, you could use compression. The problem there is if you compress data and you have errors in the compression, it might be worse than having the raw data and errors there. So for example, SSH uses compression, and then the connection just aborts if there's an error. And for Telnet, without compression, you just have corrupted bytes. So depends on your scenario. If you say, okay, I'm fine with having some corrupt bits there, use no compression, but you could also use compression, yes. Then it might be even faster. But then it, of course, depends on the data you want to compress. Yeah.
Any other questions? No, so, oh, right here.
How do you make sure that actually your two VMs are scheduled on the same hypervisor?
That's a really good question. So for our purposes, you can just buy VMs until you find two. You just let. So that's the practical approach. You buy VMs and you let the cover channel run, and if they find each other, then you're on the same physical machine. But if you just want to experiment, you get a dedicated host, and then you know that they're on the same machine. But there are also academic publications about that, about how to find instances that are on the same physical host. That's just a trivial approach. If you have a lot of money, that might be the easiest way.
So if there are no other questions, then thank you very much for your attention. Thank you very much for coming.